So let's get back to our evolution stuff, okay? So we talked about just now how natural selection, different ways that natural selection can cause a population to evolve. We did a Reese's Pieces example, which I'll go over one more time in a second, for how, looking generation to generation, how natural selection will cause a population to evolve. But now what we're going to do is, for example, previously with the Reese's Pieces stuff, we had some visual predators causing adaptation. Okay, so we know that evolutionary adaptation can happen because we had everything we needed. We had variation. Right? Our population had different colors, variation in colors. That color was heritable. Right? When they reproduced, they passed on those colors, those colored genes or alleles to their offspring. Right? So we had heritability and we had natural selection. Color mattered in this situation. There were predators using their eyes and picking out the yellow ones more than the orange ones because they can see them better against an orange background. So what we're going to do now for all of these next examples is we're going to turn off natural selection. Okay? We're going to make natural selection not happening, for example, by making the predators blind. Right? If there's no predators that can see, it doesn't really matter what color you are. All right? So now we're going to look at what else can cause a population to evolve. What else causes allele frequency to change when natural selection is not happening? Okay, so we'll go over the examples with the overheads. And I will scan the transparencies and post them online, but do so you can get the questions and the little bits of notes I wrote. But I would encourage you to take your own notes just because I won't be writing every little detail down. All right, so switching over. So last time when we left off, we had, so I turned down the list. Now you can see the orange paper is actually orange, right? So when we left off, we were looking at an evolutionist scenario where we had an orange environment, right? And we had visual predators doing natural selection, right? So it's just a review of natural selection again before we go on to the other ones. So notice that we started off with 5 orange and 5 yellow, right? Equal allele frequencies. But then because of natural selection, right? Because we had 2 predators eating the yellow ones more often, the population changed. It evolved so that there's fewer yellow ones and more orange ones. Right? So we decided together that the mechanism that's causing this evolution is natural selection. Right? The reason why is because the environment is what's causing evolution. The environment is causing the orange ones to survive and reproduce better than the yellow ones. Okay, so that's why it's natural selection. Environment causing evolution, therefore adaptations happening. Right? So another question here. So what if we have a new mutation in this population and this appears? Right? We now have an allele for brown color. All right? What's going to happen to that allele over time? It's going to go up or down? Huh? So who says that the allele frequency of brown is going to go up? Who says it's going to go down? So more people saying it's going down. And that's correct, because if you think about it, if I'm a predator, what can I see better? Right? Yes, yellow ones stand out a lot, but compared to the orange ones, the brown ones stand out as well. Okay, so over time, like notice that mutations are random, right? Mutations can cause it to turn purple, to turn yellow, to turn whatever color is possible, but it's not necessarily good for its fitness. So if it's not good for fitness, if it still stands out better, more than the orange ones, then natural selection should over time remove it, just like it removes the yellow ones. Okay? So brown alleles appear at random mutation. Natural selection should decrease them. All right? So, as a bit of a challenge question, right? What if the environment turns green, right? So what if some moss species colonizes the island and just covers everything in green, right? What needs to happen before this population can evolve to match that green color? What do we need? Anybody?
Mutation.
Yeah, we need mutation because we don't have any green alleles yet. I don't even have any green candies because these are Skittles. But we need mutation to create new alleles that are green, right? But it's not going to happen just because we want it to be green. We're going to get all these different colors just by random mutation over a long period of time. And if we're finally lucky enough for one of the mutations to make them a little bit more green, then finally natural selection can start acting on this population to make it more well adapted to this environment. Does that kind of make sense? So that's kind of the interactions between kind of natural selection and mutation to cause adaptation, right? Any questions about that? Okay. So let's turn off natural selection now. And we're going to make all of the predators blind. And we'll look at scenario 2. So as I go through this example, I want you guys to talk to your groups and decide what mechanism is causing evolution and justify your answer. Okay? So I'm going to start off with 5 and 5. And as a random predator, I'm just going to close my eyes and pick out 5 of them to kill. So the predator comes along, blindly kills 5 of them. And I'm going to note down after they reproduce what we have left. So that will be 6 orange and 4 yellow. Okay? So I'm going to keep doing this for a while just to see what happens as I continue. So 1, 2, 3, 4, 5. So talk to each other, decide exactly what kind of mechanism is causing this and why. Okay?
Is it genetic?
What's that?
It's not found in no bottleneck.
What's founder?
Isn't it when they travel to like
It's when like a small species.
yeah, so like a small group of them land on like
Yeah, bottleneck is when they kill a bunch of them. Genetic drift?
Yeah.
We're just guessing. Orange dye.
Okay, so from now on it's going to be pretty boring in that we lost all the orange alleles. So it's always just going to be 10 and 0, 10 and 0 from now on. Okay, so what did you guys come up with? What mechanism is this?
genetic drift.
Genetic drift. Very good. Why? Why is this genetic drift?
Completely random.
I'm sorry? Yeah, because it's random. Because it doesn't matter what color you are, you're still dying at the same frequency, right? Same random frequency. Because random. Also because there's no natural selection. Okay, so whenever there's no natural selection, it's going to be evolving randomly, okay, by genetic drift. So when did an allele get fixed? What day did fixation happen?
6.
So day 6. Good. But I just wanted you guys to understand the word fixation. It just means that we lost all alleles except one. So we fixed the yellow allele. That's all we have left. Okay. So here's an interesting question. So you noticed that, so this is evolution for sure because allele frequencies are changing. Almost every generation, the allele frequency is different from before. It's like 50%, 40, 40, 80, 60, 80, right? Also notice that without natural selection pushing it one way or another, it's just drifting back and forth, right? For a little while, orange went up, then orange went down, then orange went really down. Okay, so it's drifting back and forth, and sometimes it drifts so far that we lose the allele altogether, right? So this is with the population of 10 candies, right? So what if instead of 10 candies, each candy represented 1,000,000? So we have 10 million candies instead, right? Would you expect genetic drift to happen so dramatically? Who says yes? Who says no? Yeah, not at all, because, I mean, what are the chances that 2 million orange candies fail to reproduce in one generation? It's almost impossible, right? Or what are the chances that, you know, we went from 60% to 20% of orange in one generation when you have millions of them? It's much less, right? So this is why you kind of notice how for genetic drift, even though it's random, it's different depending on how big the population is. Small populations will drift very, very quickly and quite often lead to fixation, right? Whereas large populations will drift very, very slowly. Okay? One more thing to note is genetic drift was acting, as far as when it's happening, is acting throughout this time. So from, you know, day 0 to whenever. Oops, I'm drawing overhead now. Day 0 to whatever date, right? Genetic drift has been acting. Some people think that genetic drift only happens when fixation happens. That's not true. Right? As long as the population is changing randomly, genetic drift is happening. Okay, any questions about genetic drift? Okay, so next scenario. We have blind predators again, so it doesn't really matter what color you are. But I'm going to have a little bit more variation this time. I'm going to have 5 each of orange, yellow, and brown mixed up. So what's going to happen to this population, very sadly, is a meteor is going to come down, and it's going to hit the island and kill all but 2 of them. Okay, so just randomly grab all but 2 and they all die. Okay, so next generation, very easy. We have one orange, one brown. Okay, what kind of mechanism is causing evolution here? Bottleneck effect. Perfect, good job. Right? Also genetic drift, because bottleneck effect is a type of genetic drift. Okay, so that would be acceptable as well, although you wouldn't get full marks unless you gave the specific bottleneck effect. Right? So why is this bottleneck effect? Justify your choice. Anybody? Yeah, Jerry? Yep, so we have a sudden decrease in the population. Very good. So why is bottleneck effect? Why did I say it's a type of genetic drift? Why isn't this actually natural selection? Yep. Sorry?
The meteor is just random, there's no natural selection.
Yeah, exactly. So the meteor is acting, thank you, it's acting randomly. It doesn't care what color you are, right? If you get hit by the meteor, you're still going to die. Okay? So because, again, because it's random, and because this is not natural selection, right? Oops, sorry, let's go down here. Right? This must be a type of genetic drift instead. Okay? Any questions about bottleneck effect? Yeah, again, notice that evolution did happen. Right? We went from 30% of each to 50-50 of orange and brown, and we completely lost the yellow alleles as well. Huge amount of evolution, but not adaptive evolution. Right? It's just random change. Okay, next scenario. So in this one, we're going to have some islands. So we have an orange island, or orange mainland, sorry. We're going to have a bunch of little islands. Arts and crafts are fun. Okay, so on this island, we're going to start off with 5 of each again. Right? Now this time what's going to happen though, good, okay, is that a hurricane is going to come along and it's going to blow kind of a pair of candies onto each of these islands. So notice that originally these islands do not have any candies on them, okay? And we're just going to randomly have a hurricane blow through and transfer 2 onto each of these islands. Okay? So let's write down what we saw. So island 1, we have 1 orange, 1 brown. Island 2, we have 1 yellow, 1 orange. Island 3, we have 1 yellow, 1 orange. Island 4, we have 1 brown, 1 orange. Okay? So notice that evolution definitely did occur. Right? We start off with 30% of each again, and now we have 50-50 of 2 different colors. Different for every single island, it seems. Right? So what kind of mechanism is causing evolution here? Founder effect. Very good. Now some people might have said gene flow, right? Because it seems like gene flow. Why is this not gene flow? Yeah. I'm sorry?
Because there's no other genes being added to anything else with the same species.
Okay, so it's from the same species. Now, gene flow is always within the same species, but you're right that there's no other kind of individuals involved. So in other words, gene flow, it's actually a very appropriate word because if you have 2 different gene pools, you can have gene flow from one pool to the next. Okay? So 2 gene pools, so 2 different populations. If you have individuals moving over, you're basically flowing some genes out of one pool into the next pool. Right? Now we didn't have another pool here. We never had a population there at all. So what we're doing instead is we're making new populations. Okay? So it's founder effect because we're making new populations. Now this, why is this not bottleneck effect? So why does this not match bottleneck effect? Patrick?
Because the total variation of the species doesn't decrease.
Oh, interesting. Yeah, very good. So the total variation of the species isn't decreasing. We're not killing anything at all, right? And some people might say that the effect is kind of similar. Either way, we're left with a very small population that's different from before, right? But the fact that the rest of the population is still alive, right, the rest of the species is still alive is very important because if you think about it, you would think that maybe this population here is screwed because it has no yellow alleles. It's going to have to wait millions of years to mutate randomly until it gets a new yellow allele. Right? That would be true for bottleneck effect. But the fact that there's still all these other populations around means that the next time a hurricane comes along, maybe you'll be lucky enough to gain a new yellow allele. Right? So that's why it's the distinction, even though it looks similar in terms of the effect on this population, it's very different because what happens in the future is very different between bottleneck effect and founder effect. All right, great. Thanks, Patrick. So why is this a type of genetic drift instead of natural selection? So we talked about this lots of times. Anybody? What's that? Yes. Because it's random and because it's not natural selection, right? It doesn't matter what color you are, the winds are still going to blow you just as hard to somewhere else. Okay, so a challenge question for you guys to think about, right, at home is what's going to happen to these populations after this, right? Generation to generation afterwards, what's going to happen to these populations and why? And also, you'll notice that you're missing some information to answer that question. So what information would you need to gather if you were a scientist before you can make that prediction? Okay, so think about that, and you can share those answers with your TAs or with me later on. Any questions about that event? Okay, last one. So in this one, we're going to have, wait a second, 2 big islands, yellow and orange, okay? And we are going to have, so on these islands, notice that I said that there's visual predators. So natural selection is kind of acted on the past on these populations. So notice that in the yellow, okay? In the yellow island, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 yellow and 1 orange. In the orange island, we have 9 orange, 1 yellow. Okay, so natural selection has already made these populations fairly well adapted to their specific environments. So what's going to happen now is a hurricane is going to blow through again, and randomly speaking, we're going to transfer 2 individuals from island 1 to island 2. Okay, so what has just happened? What type of evolution? What mechanism of evolution?
Gene flow.
Right. Gene flow. Right, so this is definitely gene flow this time because we have 2 initial populations and we're moving genes from one pool into the next. Okay? So this is not necessarily genetic drift because generally speaking, when something is traveling from one island to the next, its genes aren't necessarily random. Right? Birds that like to fly really high, birds that like to migrate really far, they're more likely to move to the other island. So it's not entirely random. Okay? But in terms of color, it's fairly random. So I won't check out genetic drift, it's not always true. Right? So when gene flow happened, which population evolved? Right? Who says both populations? Right? Who says first one? Island 1, island 2. Both populations it is. Right? Because notice that we now have 2 fewer yellow ones here and 2 more yellow ones here. So we went from 90% down to less than that, right? And we tripled our amount of yellow on the other island. Okay, so question for you guys now is, so I want you guys to talk about this in groups. Was this adaptive evolution? Did adaptive evolution just happen? So talk to your groups, we'll give you about 20 seconds, go.
Besides this yellow one that I
Okay, time's up. So, Sam's group. Right, what are you going to say? Yes or no? No, and why? So anybody from your team? Or from the next team? Yeah, sorry, Aaron, yeah?
It was random, it wasn't like based on.
Okay. So, really, so it wasn't necessarily random. Well, I guess in this case it was because it's just hurricane blowing wind. So yes, it's random in this case, right? And it's not natural selection. But also, if you take a close look at what happened to each population, did each one get better or worse? Yeah, each one got worse, right? So this one lost some of its good alleles, right? If it's a big population, it's not a big deal. But this one definitely gained some alleles that were not good. Right? Most of the time, when you get gene flow, it's actually not good for the receiving population, right? Because you're receiving individuals that were adapted for a different environment, So when they move to your environment, they're probably not well adapted. Probably have alleles that are not so good for living in that environment. Okay, so it's generally not adaptive evolution for the receiving one. For the one sending it, it's kind of random. You're just losing alleles kind of random. Okay. All right. There's a bit of a challenge question that you can tackle at home. Is to think about, does gene flow ever cause adaptive evolution? Okay. So are there situations where gene flow will actually make the populations better than before? If not, explain why not. If so, explain how that would happen. Okay? Any questions about any of these mechanisms?